that linear algebra has in different fields. Um, and you'll see that everything that we've learned up until this point, up until everything that you've studied for exam number 2, will now come all together as one. And I think some of you may have heard this topic before in relation to linear algebra. So today is the 24th. So in a sense, if you take a linear algebra class and you don't discuss this particular topic, then almost in a sense you didn't really learn linear algebra. It's that important. It's that important. But how I want to begin is a bit of a review on polynomials, just a very brief one. Okay, so you may be like, wait, why are we reviewing polynomials? So polynomials, right? They're of the form. What kind of form are they in? They're this form. Right? And the a sub I, they're all real numbers, right? From I goes from 0 all the way to n. So each of these a sub I coefficients are real, right? Another thing is that these things here, the powers of the terms, so these are just characteristics, powers or the exponents of each term is a non-negative integer. Right? The degree is equal to n, which is the highest exponent, right? So all this stuff is just review, right? That's the degree. So with the degree, it gives you information about the polynomial. And what we're interested in polynomials particularly are finding the roots, right? We like finding the roots, or also known as the zeros, or also known as the x-intercepts, or also known as the solutions, right? These all are essentially the same thing: roots, zeros, x-intercepts, solutions, right? And that's what we care about when we talk about polynomials. Now, of course, you guys have solved these kind of polynomials, right? These are very nice polynomials that you've solved. They're quadratic. And if what you try to do is try to factor it, if you can factor it, then you can solve for the roots. If it's not factorable, then you use the quadratic formula, which means that you can still solve it. But then when you get to these kind of things, right? When you get to cubic, solving these are more involved because there is no straight up formula that we can use at the moment to find the values of the roots. So we can either graph it, or we can use a bit more high definition techniques when we have higher degree polynomials. And I don't know if some of you have heard about this, but there's something called the rational roots theorem. Is anyone familiar with the rational roots theorem? Or is this the first time you guys have heard of this theorem? It's her first time. Okay. Yeah. So this is a it's just a theorem that states that if you have a polynomial, so given a polynomial as the one we just discussed, right? So given this polynomial, uh, the potential or the possible candidates for the roots of P of X, and that should specify what kind of roots they are going to be rational. Are what? Are the factors of constant term divided by the factors of leading coefficient. So the constant term is a sub naught, and the leading term, the leading coefficient is the coefficient of the term with the highest degree, which is called the leading term. So it's the leading factors of the leading coefficient, a sub n. Okay. So let's see that in action. So let's see if I have. Let's see if I can have a good. So the idea is, let me just hold on. Yeah. So if I have a polynomial of this form, 2x to the fourth minus 5x cubed minus 4x squared minus 15x plus, pardon me, it's plus 15x minus 6, right? And I want to find the zeros. Well, in reality, when you find the zeros of a polynomial, once you're able to find it, then what you can do is factor the polynomial based upon the zeros. Okay? So the idea behind this is I want to find the roots that may be rational. I could have a polynomial whose roots are all non or irrational, right? But I'm interested in the rational ones. So what are the potential ones? So the potential rational roots. So what are the factors of the constant term? Well, of -6, right? That's my constant term. Well, what are the factors of 6? That's pretty straightforward. What do I have? I got 1, 2, 3, and 6, right? Those are my rational roots. but because of the negative, and even if it's a positive, I can also have, for example, So we're going to go, when we talk about factors, we're dealing with all possible numbers that when you multiply give you -6. So for example, I can have a -2 times +3. So the negatives are also considered factors for this case. So it's really +or -1, +or -2, +or -3, +or -6. Okay, does that make sense? And then what are the factors of the leading coefficients? 2. Well, that's nice because just 1 and 2, correct? But again, um, it could be positive or negative because, for example, you can have -1 times -2. Okay, that gives me +2. So all possible ones are always going to be plus or minus. Okay, so that's the idea. Do you guys follow me? Why is it 1 and 2? Well, what are the factors of 2? 1 and 2. 1 times 2. But it can also be negative because -1 times -2 also gives me +2. So when we're dealing with the factors for this particular kind of problem, we're dealing with all possible ways of getting two numbers to multiply to the numbers. So we're dealing with the positive and the negative numbers. And so by the rational roots theorem, all possible x values that are roots, rational, are going to be the ones that are divided by each other. Do you guys understand? So for example, take plus or -1 and divide it by plus or -1. What are you going to get? Plus or -1. So that's a potential rational root to the polynomial. Then do the same thing here. Plus or -1 divided by plus or -2. What am I going to get? Plus or minus a half. So that can also be a potential rational root. And then you continue with this idea. Plus or -1 divided by plus or -2 divided by plus or -1, I get plus or -2. Same thing. Plus or -2 divided by plus or -2 is what? Plus or -1. I already have that. Do you see how we do this? Plus or -3 divided by plus or -1 is plus or -3. Plus or -3 divided by plus or -2 is what? Plus or -3/2. Plus or -6 divided by plus or -1 is plus or -6. And then plus or -6 divided by plus or -2 is plus or -3. So in reality, what do I have? I got 2, 4, 6, 8, 10, 12. I have 12 possibilities for the root to be rational for this polynomial. I got 12. But then looking at this polynomial, do you guys know how many roots exist? It's another theorem that you should know about polynomials. Does anybody know how many roots there should be? So at most 4. It could be less, but it's at most 4. So there's something called the fundamental theorem of algebra, right? This is a fundamental theorem. Which simply put states that a polynomial of degree n has at most n real roots. Because there's this possibility that you can have complex. And that happens in quadratics, with cubics, and with every other degree polynomial, n degree polynomial. So the idea is that we can have 4 roots that are real. We can't have 12. So not all of these will work So you see, I'm building this up, okay? I'm building this idea of polynomials because we're gonna see the polynomial thing again. I just want to make sure you guys are all on the same footing when we talk about polynomials. Okay, so we discussed rational roots theorem, which is just a way to figure out all the potential roots that are rational for the polynomial. We discussed the idea of fundamental theorem of algebra, which is just a fundamental fact that a polynomial of nth degree has at most n real roots. It cannot have more than n real roots if it has degree n, but it could have less because the existence of complex roots. So the next question would be, how do we determine whether these polynomials or these roots, pardon me, these potential roots are indeed roots? What would be a way to check? How would you check if one of these is indeed a root? Anybody have an idea? What's a fundamental aspect of being a root? We can plug in the equation. That's right. If we plug it into the equation, what should be the result? It should equal 0, correct? And so if it doesn't equal 0, then what? It's not a root. So can we plug in 1 really quick? What's 1? It's just going to be what? 2 minus 5 minus 4 plus 15 minus 6. What does this equal? This equals negative 3 minus 4, right? Plus what? 9. This equals what? Negative 7 plus 9 is equals 2. This is not 0. So what do we say? X equals 1 is not a root. Agreed? And then we'll continue doing this. X equals negative 1 business, right? So does that work? P of negative 1? What's P of negative 1? This will be 2. And this will be plus 5, minus 4, minus 15, minus 6. Do you guys see already that this won't be? Because you have a more of negative numbers. This won't be 0. So then what do we say? X equals negative 1 is not a root of P of X. Now what happens when we plug in a half? Do you guys see the complication now? Because when you plug in a half, you have to square it, cube it, raise it to the 4th power. And then think about checking 6. I'm gonna do what? 6 to the 4th, 6 cubed. These are big numbers. So the question now is there a better way? Is there a better way to check? Do you guys remember a way to check that doesn't have to be including the numbers or plugging in numbers, even though that's like the most straightforward way of checking? Do you guys remember another way to check whether a number is a root of a polynomial? Linear combination. So the quadratic formula is only useful for polynomials, for polynomials of degree 2. What if I'm in degree 4? And linear combinations, for now, we're not dealing with any linear combinations. We're dealing with polynomials, which are sums of terms. Does it involve a matrix? Not yet. We're not even touching linear algebra at the moment. Right now, this is purely a little review, or I guess a little short preamble, hopefully, on polynomials. Yeah, right now, you can learn this without having to touch matrices. There's no matrix involved at the moment. This is purely a question of polynomials and polynomials only. So right now we're only talking about polynomials, and there's a reason why we're only talking about polynomials, because it will come into the world of matrices, but we're not there yet, because I don't want to go into the world of matrices and with polynomials if we don't know what polynomials are clearly beforehand. Yes, the completing the square method is only for quadratics. So as you can tell, what you've learned in terms of algebra and solving polynomials, you've only learned a very limited amount. You've only dealt with quadratic equations. Cubic equations are very far in between even. And then anything above that, we barely even touch. We barely touch. But it's important to be able to figure out how to approach polynomials of higher degree. And one way is to consider the rational roots theorem, because that breaks down a lot. At least, even though we have 12 potential numbers, we have at least 12 that we can figure out whether or not they are indeed the roots, because these are, if they are rational, they have to be one of these. That's the whole point. If you have rational roots to the polynomial, you have to have one of these being them. So if you guys don't recall that, so also recall was this idea of synthetic division. Remember synthetic division? Does anybody remember synthetic division? Remember? Synthetic division. So let's go back to our polynomial, right? 2, 4, 5. So remember synthetic division, if I wanted to divide the polynomial divided by, this case, x minus 1, remember this? The root is 1, right? The root is 1 here. And then we put some people put it, the way you write like some people put the vertical, the lines like this. They create like a little box this way. I put it this way. It doesn't matter. What matters is the coefficients of the polynomial. It's 2, -5, -4, 15, -6. So it's 2, 5, -4, -15, -6, right? Pardon me. It's -4 plus 15. Okay, so this is what it is, right? And then what do we do? Do you guys remember the procedure? We bring down the 2. 2 times 1 is what? 2. -5 times plus 2 is what? -3. And then 1 times -3 is -3. Then you add this, you get -7. 1 times -7 is -7. You add this, you get +8. 1 times 8 is what? And what do you get? -2. Does anybody remember this procedure? This should have been taught in pre-calculus, for those of you who took it. Does anybody need help with this? So I'm not, yeah, so synthetic division is just, you take the coefficients of your polynomial, and then you take the root of the factor you're dividing by. Yeah. And so the step behind this is you bring down the 2. And then you do 1 times 2, and that number you put it underneath the next number. Then you add -5 plus 2, -3. Repeat the process. 1 times -3 is -3. Add these numbers. You get -7. Repeat the process. 1 times -7 is -7. Add 8. 1 times 8 is 8. Add -2. The reason why we perform synthetic division is because instead of doing this, x minus 1 into 2x squared, 2x to the 4th minus 5x cubed minus 4x squared plus 15x minus 6. Instead of doing long division, which is the proper way to divide polynomials, right? That's the standard way. Instead of doing all of that, and this will be a very long and lengthy work, there's a simpler way to do it, and that's synthetic division. So these numbers here, when you look at these numbers, these are the coefficients of my quotient. So whatever's going to be up here is going to be x cubed minus 3x squared minus 7x plus 8. So these are the coefficients of quotients. And then what's this number? What's this last number represent? Well, we have a quotient when we divide, right? When we divide a polynomial by a polynomial or a number by a number, we get the quotient plus a remainder. Now you're like, wait a minute. You're talking about linear algebra, but then you went to polynomial world, and then you're talking about rational roots, and then all of a sudden you're talking about synthetic division, and now we're talking about quotients and remainders. Like it seems as though we're going farther away, right, from the original place that we were in. But the reason why I do this is because if you notice, what do you notice? Yeah, the top left is just the root that you're testing. That's right. So let me just see something. If I did this correct. Oh, I added incorrectly. Guys, you gotta tell me. -6 plus 8 is +2, not -2. Okay. If you notice, I divided the polynomial by x minus 1, where 1 is the associated root, right, to this x minus 1 factor, correct? And when I performed synthetic division, I divided my polynomial by this polynomial, and I got this. But what I'm not interested in actually what the coefficient of the quotient is. What I'm interested in is the remainder. And this is another thing. The remainder is 2 when you divide it by x minus 1, right? Which is associated with the root being 1, quote unquote, right? When I plugged in 1, what did I get? I got 2. So there's something called the remainder theorem. Okay, another theorem that I feel that you guys should know. But if you don't, I'll remind you or teach you for the first time. There's something called the remainder theorem. And the remainder theorem states that if a polynomial p of x is divided by x minus a, then p of a equals the remainder of p of x divided by x minus a. That's right, Sam. That's the whole point of all of this. The point is that, for example, if I wanted to test whether 6 was a root, the straightforward way is to plug in 6, right, into my polynomial. So I would have to plug in 6 every single time I see x. And I would have these huge numbers to worry about, 6 to the 4th, 6 cubed. Of course, if you have a calculator, no problem. But let's say you don't have a calculator. Let's say you don't want to plug in these things into your calculator. Then there must be a better way. And the other way is to say, well, what if I divide by x minus 6? I can perform synthetic division. And synthetic division is very straightforward. It's not much of a complication, right? We're just adding and multiplying numbers. So the idea, what's the idea? The idea associated with this remainder theorem is if you are indeed a factor, then the remainder should be what? 0. And vice versa. If my remainder is 0, then the original factor, then the original divisor is indeed a factor of my polynomial. This idea of factorization is an essential aspect of algebra in general, just the general sense of algebra, right? When you learn algebra, you learn several skills. There's 3 main skills. One of them is solving equations. So there's simplifying expressions, right? So that's what you learn in algebra. You learn how to simplify all types of expressions whether it be complex fractions, whether it be rational expressions, all these different expressions, you learn how to simplify, simplify, simplify. And then you learn how to solve, right? You learn how to solve quadratics, you learn how to solve rational equations, you learn how to solve radical equations, you learn how to solve equations, solve equations. And embedded in all of that is learning how to factor, factorization. This idea doesn't go away. The idea of factoring doesn't go away as you continue. Actually, you'll see you can actually factorize, you can factor matrices. That's where we're headed. We're headed into that world of factoring matrices. But regardless. So for example, if I want to test, for example, 6, right? I want to test whether x equals 6 is a root of p of x. One way is to say, what's p of 6, right? What does that equal? But according to my theorem, the value of my polynomial at 6 is equivalent to finding the remainder of my polynomial divided by x minus 6. Do you guys see that? That's the remainder theorem. And I want the remainder to be 0. I'm testing whether it equals 0. If my remainder is 0, then my polynomial at 6 is 0, which means that 6 is a root. If it's not 0, then it's not a root. So do you see how I can circumnavigate the idea of multiplying huge numbers and adding them together and just add and just deal with the coefficients themselves? So this will be 2, right? This is 2, -5. Or is it -4? 15 and 6. And all I'm doing is I'm dividing this by, right, using 6, right? So bring down the 2, you get 2. 2 times 6 is 12. You add this, you get what? 7. 6 times 7 is 42. You add this and you get what? 38. So yeah, eventually you do have to multiply big numbers, but it's not so big. It's decent amount, right? And then 6 times 38, you get what? You get 48, and then you get 228. So obviously, what's going to happen when you add these together? You're going to get what? 243. And then when you multiply this, what's the idea though? Even if you don't have to multiply this all out, what's the idea? Will this be 0? It won't be 0, right? So it's not 0. What does that mean? X equals 6 is what? It's not a root. Do you guys see that? I don't really care so much what the value is. I just care whether or not it does equal 0. Obviously, it's not going to equal 0 because I'm adding a big positive number with another positive number, so it's not going to be 0. But the connection and the idea is what's important. Okay? So then that's the idea behind synthetic division and how it's related to rational roots theorem and how that's related to finding the roots of a polynomial. So you can go on and on with this. You can plug in 2, plug in 3, and then you start to see maybe 3 halves might be one of them. It could be plus or minus a half. Okay, so that's the extent. I don't want to continue with this whole thing. I just want to make sure you make the connection, because these tools are going to be useful, maybe useful for what's coming next. Okay, I just wanted to make sure you guys have an idea of how to deal with polynomials, just purely polynomials. And I feel like that's something that is not stressed enough, how to solve polynomials of degree higher than 2. Because quadratic equations are we really know how to deal with them. Quadratic formula, completing the square, factor. But what if we have a cubic? What if we have a quartic? What if we have a quintic? What if we have higher degrees? Okay. So that's the preamble for this lecture. It's just polynomials. So now after we've discussed that, let's talk about what we want to talk about today. And what we want to talk about today is the beautiful idea, the concept of eigenvalues and eigenvectors. Have you guys heard of this term? Have you guys heard of eigenvalues, eigenvectors? Yes. This is a beautiful, like, oh, I have said this already. Oh, yeah, I may have mentioned it here and there, right? So, eigen, the word eigen is German. It's a German word that means several things. Own, peculiar to. So this is from your textbook. Characteristic, individual. So it's important sometimes to understand the etymology of words, especially with mathematics. Understand where the word this is derived from, because a lot of these symbols, these words come from a particular culture, nation, in a particular time of the history. So as much as people tend to think math is just some isolated subject in a room somewhere inside a textbook, it's actually a human endeavor. So a lot of these things have more than just significances beyond mathematics, right? So this idea of eigenvalues is a central theme in linear algebra. So let's define it. Let's define it. What does this mean? So, okay, if A is an n by n, so this is important. Remember we discussed matrices for the first time. There's several ways to group or to categorize matrices. One such categorization is you have all matrices that are square and non-square, right? So you have all these groups of square matrices, which means that you have the same number of rows, the same number of columns. And then you have matrices where the number of rows and columns are not the same. And within that set of square matrices, you have matrices that are invertible and non-invertible. This idea of invertibility is particularly discussed with square matrices. Okay, so for now, this world of eigenvalues, eigenvectors, we're going to be particularly dealing with square matrices. Okay, so non-square matrices we've discussed and we've learned how to deal with that. But we're talking about particularly square matrices in this case. So if A is an n by n matrix, then a non-zero vector, I'm gonna call it V. V in Rn. So again, we're dealing with Rn. So we have a non-zero vector, important to note that it's non-zero. It's a non-zero vector in Rn. This is called an eigenvector. It's called an eigenvector of A. And don't forget that A is also a matrix representation, right? It's a representation of what? Of a linear operator, or in this case, a transformation. Don't forget that. That's going to come up again too. This idea of transformations, okay? So matrices are not just matrices. They're not just entries of numbers. The matrices are also representative of a linear operator or a linear transformation from one space to another. So that's another way that we have to consider matrices, okay? So it's called an eigenvector. Why is it called an eigenvector? Um, when this happens, when if you multiply a matrix A, the matrix A you're dealing with, if you multiply it by this vector, what you get is the same thing as if you were to take that vector and multiply it by a scalar, and this scalar is called lambda, right? This is what we called the this is just lambda in it's a Greek letter, right? Lambda, and this lambda is considered the eigenvalue. So this is a scalar. Okay, I'm just write this as a scalar. You may be saying, "What? This is it? That's all it is?" This is very profound, actually, because if you consider the geometric understanding of this, this is saying that if you take a vector v and you multiply it by a matrix A, then it's the same as if you just scalar multiplied this vector by a particular number. Normally, that's not true. Normally, when you take a vector and you multiply it by a matrix, you get something just completely outside, like completely different. It's a completely different vector. But when you find an eigenvector, which is a particular, that's why eigen, right? Peculiar to, characteristic, individual. There's a particular eigenvector associated with this matrix that when you multiply this eigenvector by that matrix, it's equivalent to getting a scalar multiple of that vector. And that's pretty significant in the world of linear algebra. So it's called an eigenvector of A when this is true for some scalar, right? For some scalar lambda, the scalar lambda is called the eigenvalue it's called the eigenvalue of A. And we say that V is the eigenvector corresponding or associated to lambda. Okay, so it's a lot. It's a lot to take in all at once. This idea of eigenvalue, eigenvectors, they're connected. You can't talk about eigenvalues without talking about eigenvectors and vice versa. So what we're saying is every matrix, well, there's matrices, right? They have an eigenvector, and if they have an eigenvector, there's an eigenvalue associated with it. So far, all we've done is define it. Okay? Okay, so an example. Suppose we have a 2 by 2 matrix, 3, 0, 8, -1. Okay? And then I have an eigenvector, 1, 2. What happens when I multiply A times V? What do I get? I get 3, 0, 8, -1, multiplied by 1, 2. And when I do that, what do I get? I get 3, and then I get 6. But what is 3, 6? Isn't that just a scalar multiple of the eigenvector 1, 2? Or should I say 3? 3 times the eigenvector? Right? So what do we say? We call this an eigenvector of A. Why is it called an eigenvector of A? Because when you multiply by that matrix A, you get a scalar multiple of that vector. And 3 is the what? 3 is the eigenvalue. What if I do this with another vector, call it W? What if W is 3, 4? What would I get instead? I'll get 9. And then I get what? 20. I get 20. Is this a scalar multiple of W? Is there a way that I can multiply W by a number here? By a number, we'll call it question mark. Is there a number that multiply by W, 3/4, gets me 9/20? Well, to get 3 to become 9, you have to multiply by 3, correct? But 4 times 3 does not give me 20. So then what do we say? 3/4 is not, do you guys see that? Is not an eigenvector of A. Why is it not an eigenvector? Because if it doesn't, when I multiply A by that vector, I don't get a scalar multiple of that vector. Does that make sense? So eigenvectors are very particular. They're not just any vector. They're very specific ones. Now, what do you think? What do you think it's the natural question from here? What do you think we're going to be considering now? I gave you this eigenvector. But what if I don't? The question would be, how do you find them? Like, how did somebody say, oh yeah, the eigenvector is 1, 2? Like, there's so many to choose. There's so many vectors out there to choose from. How do you know that this was the one indeed? Was it just by pure luck? So the answer obviously is no. So then how do we find them? How do we find the eigenvalues? How do we find eigenvectors? That should be the next question. So how to find the eigenvectors so this is really the crux of the issue here. If you give me a square matrix, the idea is that I can figure out the eigenvalues for eigenvectors because the word eigen means particular, peculiar to, characteristic of. So there seems to be a connection between every matrix, square matrix, and the eigenvectors and eigenvalues. There seems to be a connection that every matrix has a particular eigenvalue or eigenvector associated with that matrix. So all we have so far is that A times some vector V, some vector, equals lambda times V, right? And I hope you start to see how things start to now come together. So this is an equation, right? This is an equation. Normally, I know A. Okay, I know this. So this is given. What does V have to be again? What's the first thing I underline in the definition? It had to be what? What does V have to be? And that's pretty important. Non-zero. That's pretty important. If it's non-zero, it cannot be zero, right? One of the entries cannot be zero. One of the entries has to be non-zero. Okay. And then, so that's unknown, right? It's an unknown value. I don't know what that is. And what else don't I know? Scalar, right? I don't know this scalar. So seemingly, it looks like I have an equation with two unknowns and only one known value, seemingly. So what do we normally try to do when we solve equations? What do we normally do? When they teach you in algebra, what do they always tell you to do when you solve an equation? You set it equal to what? Um, it equals zero, guys. Yeah. So lambda, yes. I see what you're going with the lambda. We do try to solve for the unknown, right? But normally the straightforward, the standard way, even if you have a quadratic, is you set it equal to zero. So let's set it equal to zero. So it seems as though you're like, we're getting the same equation. There's not much to say. But like I said, this is why we learn algebra, because we want to learn how to simplify expressions. We want to learn how to solve equations. And one way to solve equations is by using this technique of factoring. So you notice on the left side of this equation now, what can you factor? You can factor out the v, can't you? Oh, wow. See, you guys already have the gist of what's happening. So when I factor out, now this is where things get interesting. You factor out v, right? Okay. If I factor out v, I'm left with a, aren't I? Minus lambda, correct? Multiplied by v, right? This equals zero, correct? Is that right? But there's something wrong with this. Do you guys see what's wrong with this? It's not wrong to factor. You can factor out the v. We can do that. But there's something wrong with, and in doing so right here, right now, there's something missing in the term that's within the parentheses. Now, I just want to make you guys see if you guys can point out what exactly is wrong. Why am I saying that this is, at the moment, the way it's written, something that's incomplete, so it's wrong, it's incorrect. So consider what's inside the parentheses and consider what you're subtracting. What are you subtracting? Aren't you subtracting a n by n matrix A? What's lambda again? Scalar, right? Can't you, right? You can't subtract a matrix with the scalar. It doesn't make sense to do so. You would have to subtract by another n by n matrix, correct? So how do we account for that? And this is where things get kind of interesting. Lambda unit matrix, the identity matrix. That's what's missing, guys. There's an identity matrix that has to appear. And you need to think about, why is that true? So then think about that. Lambda v. Is that the same thing as lambda times the identity times v? Is it the same? Well, obviously it is. Why? Because the identity times any matrix is itself, it's that thing. That's the whole point of the identity, right? The identity, when you multiply it by a vector by a matrix, you get back that vector or matrix. So this does equal V. So hidden behind this multiplication is a multiplication of the identity. This is kind of like when you do like x squared minus x, right? When you factor out the x, what's left? X minus what? 1. But the 1 in matrix world is the identity. Do you guys see? Do you guys see the consistency of algebra beyond just the simple expressions that we learned in algebra 1 and 2? This idea of 1 is universal in the world of algebraic structures. And here we're talking about matrix algebra. But the idea of algebra is still consistent. The idea of 1 in our algebra world is the identity matrix. That's why this identity matrix has to pop out. Because now this becomes a what? An n by n matrix multiplied by scalar. That's good. The identity matrix is a diagonal matrix where the entries along the diagonal are all ones and every zeros everywhere else. You guys see where I'm going with this? So when you multiply by the scalar, then every matrix, the diagonal entry of every of the identity matrix now has lambda in it. And so this is going to be lambda, lambda, dot, 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 lambda, and all this is zeros, and you can subtract that with a. So now I can do that because I have an n by n matrix subtracted by an n by n matrix. And so the diagonals of A, the diagonals of my matrix A are going to be subtracted by lambda. So far, so good. So that one little step here is already, we're already dealing with something higher level in linear algebra, already with this one single step of factoring V. Now, if you pay a little bit more pay more attention to this, what kind of equation is this? When you set something to 0 like this, and again, this 0, right? In this case, is going to be called, this is a 0 matrix. This is a 0 matrix. Why? Because we have a, well, actually, it's going to be not a matrix. It's going to be a matrix, but it's going to be a vector. This is a 0 vector. Why? This is a vector, right? When you multiply, and this is a vector when you multiply. It's going to be an n by 1 vector minus an n by 1 vector. That's going to give you a n by 1 vector, but they're all zeros. What kind of equation is this? When you set something, no, it's not a polynomial yet. We're not doing polynomials yet, not yet. I'm talking about in the world of matrices. When you have a system of equations or a system that it all equals 0, it's homogeneous. Uh-oh. I told you everything's going to come back together, guys. Everything's going to go. So we went from equation to now we have a homogeneous system. Whoa. Already that quickly. That's right. Already that quickly. We're dealing with systems. So we're dealing with a system that's a homogeneous system. Think about this as an n by n matrix, right? Because this is a matrix n by n minus n by n matrix. So this entire subtraction here, this difference will be an n by n matrix, correct? This whole thing is an n by n matrix multiplied by a vector. Again, I stress this again, non-zero. The reason why I stress this is because we're going to get to y. We're going to get to y. If you have a n by n matrix and you multiply by non-zero vector, I should say vector, and the result is 0, is there anything you can tell me about that n by n matrix? This is when you have to think about those equivalent statements that we discussed. This is where the beauty of linear algebra is kind of starting to come out. The inverse of V. So the inverse, wait, no. So you're dealing with invertibility, okay. Think about an invertible matrix, okay? Let's think about the matrix, okay? M. Okay, let's call this invertible. Okay? If it's invertible and you multiply and you want to find what this is here, right? If M is invertible, what does it mean by X? What does X have to be then? Anybody? If M is invertible and you're multiplying by a vector X and you're setting it equal to 0, you have a homogeneous system, correct? And we're saying that M is invertible. So what does that mean about the solution to this system? What does X have to be then? No. What? So okay, I guess I'm not making my question clear. What does it mean to be invertible again? Invertible means that the inverse exists, right? M inverse exists. Okay, good. So M inverse exists. Okay. So guys, we have to know this. Okay. We have to know the equivalent statements like the back of our hand. Like this has to be it. When I say invertibility, remember I mentioned this, all that list of statements that are equivalent, you have to have on the spot. So if you have an invertible matrix, what else is true? Inverse exists. What else is true? Remember this? The determinant is what? What's the determinant of M? If you have an invertible matrix. Not 0. That's important. So that's important. So invertibility of a matrix means the determinant is non-zero. What does that make? An invertible matrix in a homogeneous system as the one that I've just written here, what does that mean about the solution to the system? Maybe I didn't stress this enough. But when I try to solve this, right? When I try to solve this, well, how would I solve it? I would multiply both sides by what? The inverse? No. So be careful with that statement, Sam. So this is why we're going over this. X has to be 0, right? Because when I multiply this, right, X has an inverse. So this is M inverse of times 0. But 0 times anything will be 0. What is 0 here? This is called the trivial solution. To the what? To the homogeneous system. So guys, you have to know this again. If M is invertible, that's 1. M is invertible. 2, determinant is non-zero. In a homogeneous system, mx equals 0, only the trivial solution exists. And then Sam, what you're saying is in a non-homogeneous system. Do you guys see this? In a non-homo, I think you could put this together. In a non-homogeneous system, mx equals b, there only exists, I should say, a unique solution exists. So what's the idea? The idea with invertible matrices is that when you have a system, there's a unique solution. If it's homogeneous, the unique solution is the trivial solution. In a non-homogeneous system, there just exists a unique solution. That's the idea. Does that make sense? So compare that to this. I'm saying that a matrix times a non-zero vector is 0. If this matrix that I have here inside this here, parentheses, if this matrix were to be invertible, for this homogeneous system, V would have to be what? It would have to be 0 only. But I'm saying that this vector is non-zero. So what's the implication to this matrix? Do you guys see how I'm using these equivalent statements and I'm looking at the converse, I'm looking at the opposite. If M is invertible, mx equals 0 means that the only trivial solution exists. So if it's not invertible, that's the way you start to think about. So what if M is not invertible? Then that means that in the homogeneous system, the trivial solution is not the only thing that exists. There's a non-trivial solution to the homogeneous system. Do you guys see what I'm going with this? So from here, the opposite, think of the opposite. So if M is not invertible, then mx, this system here, has a non-trivial solution. In other words, it's non-zero. When I write this, do you see how there's more than just a minus lambda I v equals 0? There's more to it. There's a significance behind it. What I'm saying is that for this homogeneous system, there's a non-trivial solution that exists. In order for that to be true, that means that this matrix must be non-invertible. If this matrix is non-invertible, that implies that, like Mir says, the determinant of this matrix must equal 0. And that's what we're going to be using, guys. That's why from here, we're going to say this. From here, we're going to say that the determinant of a minus lambda I equals 0. And so you're like, wait, what in the world? We just went from matrices, homogeneous systems, invertibility, non-invertibility, and now we're talking about determinants. Do you see how all of this stuff is all compacted now together? And all we want to do is to figure out an eigenvalue, an eigenvector of a matrix. And all of this is now combined together. Do you, do you guys see how nice this is? Because everything that we've learned seemingly was like, okay, determinants is over here. We're gonna learn about determinants, the properties of the determinants, that's over there. And then we talk about the reduced echelon form, that's over there. And then we can talk about invertibility, that's over here. We're talking about solving systems, that's over there, right? And then we see a little bit of connection. But now we talk about one single thing, an eigenvalue, eigenvector. And all of a sudden, all those things start to now coalesce together. They have to come together. So in trying to find an eigenvalue, I have to understand all of these equivalent statements of invertibility, or I should say non-invertibility as well. So the question, to find the eigenvalue or eigenvector of it, and first we're going to talk about finding eigenvalues first, and then associated with that are the eigenvectors. So to find the eigenvalues of A, from this equation, which is the way we defined eigenvalues and eigenvectors, we get this result. We get that the determinant of A minus lambda I must equal 0. And so now this here, when you take the determinant of this matrix, you get a polynomial. And then the whole point of me talking about polynomials comes right here. Boom. It's beautiful. When you see the whole picture, I think that's why people define mathematics to be beautiful. I know beauty is, like people say, is in the eye of the beholder, and there's different degrees of beauty, right? But one reason why people describe mathematics as beautiful is when you see everything together come, like when you see a puzzle, all the pieces come together, it's kind of satisfying, right? This kind of like, oh wow, that's nice. So one of those kind of feelings. Okay, so let's go back to our example that we originally had, this 2 by 2 example, right? So we got 3, 0, and what was it, 8, negative 2? And let's make believe I never saw the eigenvector, and I never saw the eigenvalue. I already know what one of them will be. But now let's see this in action. So I want to find the eigenvalues. What does that entail? The determinant of A minus lambda I equals 0. Well, what is A minus lambda I? Remember, A here is a 2 by 2, right? So if A is a 2 by 2 matrix, then the identity has to be 2 by 2. So I get 3, 0, 8, negative 2 minus lambda 1, 0, 0, 1. And so what does this become? 3 minus lambda 0, 8, negative 2 minus lambda. Whoops. Everyone follow me so far? So A minus lambda I is this 2 by 2 matrix, but I want to find the determinant. So I want to find the determinant of 3 minus lambda, 8, 0, and negative 2 minus lambda. What's so nice about this? Well, it's a lower triangular matrix. When you have a triangular matrix and you want to find the determinant, what we learned was that you only have to multiply the diagonal entries. So the determinant of this matrix is what? 3 minus lambda multiplied by negative 2 minus lambda. What's nice about this is I already found the character. So this here is what's called the characteristic polynomial. So let me just say that here, when you actually evaluate the determinant, this gives the what's called the characteristic polynomial of A. Wait. Sorry, this is negative 1. Not negative 2. So this is minus 1. This would be minus 1. This would be minus 1. This is going to be minus 1. Okay? So this is my characteristic polynomial. Of A. Solving this, I don't have to distribute everything. It's already factored for me. I want to solve it. I want to solve this equation. How do you solve this? Lambda equals 3. Didn't we find that already? Oh, well, that's what they gave us. Lambda equals 3. What does lambda also equal? Lambda also equals what? -1. Does everybody see this? So what are the eigenvalues of A? Does everybody see that? Any questions? Any concerns about this? Does everybody follow the procedure here? I'm given a matrix. Yes, Mir.
I don't understand how it has something to do with A. Shouldn't it have to do with V as well?
Say that one more time.
The lambda is the eigenvalue of A in relation to V, right?
Yes.
Okay. Okay.
Yes, because so far at the moment we've only found the eigenvalues. So this is a procedure to find the eigenvalues of a matrix without even discussing the eigenvector yet. Because we'll go back to this. We're dealing with eigenvectors and eigenvalues at the same time. But in doing so, the idea is, how do you find one of them? How do you find the eigenvalue? How do you find the eigenvector? So based upon this little derivation here, in a sense, we can kind of forget about the eigenvector in so much as to find the eigenvalue. Like I said, we started with an equation with two unknowns. That's a problem. Well, it came to a point where this idea of finding the eigenvector is not so much necessary at the moment, because the idea of having a non-zero eigenvector or a non-zero vector in this homogeneous system is tantamount, is equivalent to saying that the determinant of this matrix is 0. The reason why this is good, the reason why this statement is nice, is because in a sense we don't worry about the eigenvalue, the eigenvector, so much. We worry about this equation here, and performing this determinant upon this matrix results in a polynomial. It results in a polynomial which we could solve, and the unknown is the only eigenvalue. The only thing that's unknown here are the eigenvalues, which we can find. So once we find the eigenvalues, the next question is find the eigenvectors. That's the next thing. So if my eigenvalue equals 3, how do you find the eigenvector? Well, go back to the beginning of this. See, that's why it's important to go back. This number here, lambda, arose from this system having a non-zero solution to the homogeneous system. And what matrix does that come from? It comes from when lambda is 3. So what I'm going to do is replace the lambda with 3. And what happens when I do that? What happens? So remember, what does A represent? 3, 0, 8, -1. Subtract that by 3, 3, 0, 0. And this whole thing here is V, right? When you subtract this, what do you get? You get 0, 0, you get 8, and you get -4. Do you still have a question?
No, sorry.
No? Okay. Now, what does this problem result in? The problem of finding the eigenvector results in what? Solving a homogeneous system. What's my matrix? How do you solve it? Remember how you solve this? Row reduced echelon form. Oh my goodness. Coming back. Everything is just coming together. What? What's the row reduced echelon form of this? Usually we put the zeros in the bottom so we can switch, right? We can switch the rows. And you get 8, -4, 0, 0. And then if you really want to go all out and get the row reduced echelon form, this becomes what? 1 and -1/2. And this is 0, 0. Correct? What do we know? X1, X2. What is X1? Pivot variable. This is half of X2. What is X2? Free variable. Call it T. This is 1/2 T. So what is X? Or I should say, what is V? V is 1/2 T times T, which is written as T, 1/2 1. What did we just discuss, guys? We're talking about the null space. Oh my goodness. You're like, no way, Jose. You're like, no way, Jose. You're like, what? We're talking about null spaces now? I told you. I'm telling you, everything is going to combine and collide together with this one little thing. That's why it's so central. It's so central to linear algebra. This idea of eigenvalues, eigenvectors brings everything together. That's why I'm like, I hope I do this justice, because like I said, if you don't learn this, if you take a linear algebra course and you don't talk about eigenvalues and eigenvectors, it's as if you didn't take linear algebra. It's like you, everything you've learned is for nothing. So the idea of this is a null space that does not only contain the trivial solution, it's a non-zero vector, and this is the basis. Oh, here we go. We gotta talk about bases now, because then we have eigenbases. We're not there yet. We're not there yet. But this is a basis, right? If I gave you this problem here, just straight up, forget about everything beforehand, just straight up, you would solve this system, right? And then you would have a non-trivial solution. This is the eigenvector, guys. But the reason why now this is there's more significance to it is because we're dealing with all of this original idea. The idea, this is where all this stems from, is from this statement. That's how powerful that statement is. And so my eigenvector is 1/2 1. Or you can multiply a scalar of this, multiply this all by 2. And what do you get? And isn't this exactly the eigenvector that was said to be the eigenvector of A? 1, 2, 3, 6, 5, 10. They're all the same because they're a scalar multiple of that eigenvector. The point is, any scalar multiple of this vector, when you multiply by A, will result in a scalar multiple of that vector. That's the significance. That's the important thing. And as you can tell, you can give me another vector, but if it's not 1, 2, if it's not 1, 2, meaning that the x value and the y values are in the 1 to 2 ratio, if it's not in this ratio, I will not get a vector that's a scalar multiple of the original vector. I won't get it. As I showed with this 3, 4, doesn't work. That's why this is not a quote unquote trivial thing. This is very significant that you have such a vector that exists for A, that when I multiply by A, it's just a scalar multiple of that vector. Not everything works that way, only the eigenvectors. And so the eigenvector is this one. Boom, I got it. And 1, 2, or 1/2, or whatever scalar multiple of this vector is an eigenvector associated with lambda equaling to 3. But of course, lambda equals 3 is not the only eigenvalue. There's also a -1. So guess what we're going to do for this? We're going to say, what happens, what is the eigenvector for lambda equaling -1? Do the same exact thing. A minus lambda I multiplied by V equals 0. Well, now lambda is going to be -1. So this is going to be A plus I is V times V 0. Homogeneous system. What's going to be my matrix? It's going to be 4, 0, 9, 0. And then what's going to be the eigenvector, or how do you solve this system? Well, you look at the row reduced echelon form. What's the row reduced echelon form? Oh, yeah, sorry. I don't know why I put, it's 8. Thank you. So what's the row reduced echelon form for this matrix? Right. But what does this information from the row reduced echelon form of the matrix tell me? X1 has to be what? X1 has to be what? 0? What does X2 have to be? What is X2? T, that's right. It's free. It's free. This is free. It's roaming. This one is pivot. So then what's going to be the solution? The solution will be what? T multiplied by 0, 1. What is 0, 1? Yeah, it's not 0. Do you see that? Right. And so hopefully now you start to appreciate the derivation of all of this. It's not to our surprise that this matrix will be non-invertible. That's the whole point. You must have a non-invertible matrix in order for the homogeneous system to have a non-trivial solution. This is non-trivial. The trivial solution always works for a homogeneous system. It's just that now we're dealing with non-trivial solutions that only are associated with non-invertible matrices. If this matrix was invertible, the only solution you would get from this system is the trivial one. So I hope you guys make that clear inside your heads. Invertible matrices for a homogeneous system only produces the trivial solution. It's kind of like the boring case. It's expected. The more interesting case is when you have a non-invertible matrix in a homogeneous system that gives you a non-trivial solution. It must be non-trivial based upon the row reduced echelon form, based upon the free variables that will exist, based upon the fact that you don't have all the pivots available. That's the whole point. That's how everything is connected. And so now with 0, 1, it becomes what? What is 0, 1? It's the eigenvector of A. Associated to what? Associated to lambda being -1. So we found them. So let's look at this. What if I multiply A times my vector? So this is 3, 0. This is 8, -1. What if I multiply this by 0, 1? What would I get? 0, -1. Isn't this -1 times 0, 1? Isn't this -1 times V? Checks out. This is indeed an eigenvector. Beautiful, isn't it? What do you guys think about this? So it took us to the 20th lecture to come across this profound idea. And this is just the beginning of it. It's not even like I said, this is just the beginning. And that's why linear algebra is worthwhile to study, even just for the sake of it, because there's so much behind it. And then you talk about all the applications that stem from this is ridiculous. It's like, it's ridiculous how much of the real world utilizes this idea. It's in computer vision, it's in computer graphics, it's in physics, it's in optics, it's in a whole slew of different fields. This one little concept. Okay. Okay, so that we've done the easy case, right? 2 by 2 is pretty simple. And it was also simple because the matrix that we got for the determinant was also lower triangular. So the determinant was very easy to find. But of course, this is not a common thing. You're not going to always get lower triangular or upper triangular matrices. So let's see that. Yeah. Okay, so what if I have A zero, zero, negative 2, 1, 2, 1, 1, 0, 3. I want to find eigenvalues and eigenvectors of A. So the first order of business is to find the eigenvalues. That's the first thing we find. And then once we find eigenvalues, we can find the eigenvectors. So to find the eigenvalues, of A, I need to solve the characteristic polynomial of A, which is given by the determinant of A minus lambda I. Right? That's how we do it. Okay. What is that going to look like, though? That's going to look like negative lambda, 2 minus lambda, 3 minus lambda, 0, 1, negative 2, 0, 1, 1. The determinant of this has to be 0. Uh-oh. Uh-oh. So I guess all of those techniques that we learned to find a determinant pays off. Because how do you find the determinant of a matrix like this? What would you do? It's not going to be just a product of the diagonals. I have to actually, right, cofactor expansion, right? That would be the best bet. So then I can run, you can run, right? Well, yeah, you can either fight or flight, right? Fight or take flight. But let's fight this out. Or what's the name of that other method? Which other method? There's a trick, remember, for 3x3 matrices? Oh, Kramer's rule. But Kramer's rule is utilized. Could we do that? The thing is that comes from if you're solving a system. That's if you're solving a system and the assumption is that that system has a unique solution. So this problem, you don't have a unique solution by the very definition of having the determinant being 0. So cofactor expansion would be the best bet. Now the question is, the question would be, where am I going to apply the cofactor expansion to? Is it the first row, second row, third row? Is it the first column, second column, third column? There's going to be one, usually there's one way that's more convenient than the rest. And you should be able to spot which column or row I should do the cofactor expansion upon. It's going to be the column or row that has the most zeros in it, because those zeros clear out the determinants that you have to figure, the sub matrices that you have to figure out. So how would I perform this? So along which row column should I expand this upon? Should I apply a cofactor expansion? The middle column, right? Along the second column. So why is that? Do you guys remember how we go about this? So the determinant of A minus lambda I is going to be equal to what? If I do this along this column here, this is going to look like what? This is going to look like A12 times C12 plus A22 times C22 plus A32 times C32. Now, what is A112? This is 0. This is 0. So really, I only have to do this once. This is A22 times C22. But remember what C was? Cij? Remember what this was? This was -1 to the I plus j multiplied by the m of ij. And m of ij is the determinant of the submatrix that's crossing out the ith row in the jth column. So A22 is what? A22 is 2 minus lambda. Now, if I do C22, this will equal -1, 2 plus 2, which is 4, but -1 to the 4th power is just 1. So this is equal to M22. But what is M22? M22 is the determinant of the submatrix when you cross out the second row and the second column, the second row. And I get negative lambda, -2, 1, 3 minus lambda. And then what do? I find the determinant of the 2x2 matrix, which from there on, it's actually not that bad, right? This becomes what? Negative lambda times 3 minus lambda minus -2 times 1, which is +2. This equals 0. Everybody with me so far with this? With the expansion along the second column, we're finding the determinant. And so this becomes 2 minus lambda. This becomes -3 lambda plus lambda squared plus 2 equals 0. Let me fix this up. this becomes lambda squared minus 3 lambda plus 2 equals 0. Can I continue factoring lambda squared minus 3 lambda plus 2? What does that factor into? Anybody? 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 What does lambda squared minus 3 lambda plus 2 become? Right. So this is 2 minus lambda, and this is lambda minus 2, lambda minus 1. Right? Isn't it minus 1? So then what? So then if you really want to you can take out the negative here and you get lambda minus 2, lambda minus 2, lambda minus 1. So you get lambda minus 2 squared, lambda minus 1 equals 0. You only have two eigenvalues in this case. So the lambda eigenvalue, lambda equals 2 and lambda equals 1. So the eigenvalues of A are lambda equaling 1 and 2. Now, the interesting thing is that there's only two eigenvalues in a 3 by 3 case. That can happen. You can have eigenvalues that are less than the number of rows or columns of your matrix. So that's going to be interesting when we talk about the eigenvectors. So what are the eigenvectors? What happens when lambda equals 1? What kind of matrix do I have? I got A minus lambda I, or I should say A minus I, multiplied by V gives me 0. So what does A minus I become? Well, A is what? This becomes negative 1, this becomes 1, this becomes 2, and this is 1, negative 2, 0, 1, 1. If you notice, I'm expected to get a non-invertible matrix. So the row reduced echelon form will not be the identity, and one of the rows, as you start to see, is just a scalar multiple of the other one. So I can get rid of this last row here very easily, and this becomes 1, 0, 2. This is 1, 1, 1, 0, 0, 0. Do you guys see that? And then to get rid of this 1 here, I have to subtract row 1 with row 2. And what do I get as a result? I get 1, 0, 2, subtract, I get 0, I get 1, and I get negative 1, 0, 0. All right. Okay. So then what do I get? I got two pivot variables. And I got one free variable. So I got x1 equals negative 2x3, x2 equals positive x3, and x3 equals t or whatever. So this equals t, this equals negative 2t. So what is the eigenvector look like? Well, it's a scalar multiple of negative 2, 1, 1. So what's the eigenvector? The eigenvector associated to eigenvalue 1 is negative 2, 1, 1. So that's going to be my eigenvector. Okay, and then let's look at the last one. When the lambda is 2, what happens here? Well, this becomes a minus 2I times v equals 0, which means what? I'm subtracting by 2, right? So this becomes negative 2, this becomes 0, and this becomes 1. And then this becomes 1, 1. This is 1, 0. And this is 0, negative 2. But wait a minute. Wait a minute. This is repeated. And this is just a scalar multiple of this. So what is my row reduced echelon form? It's 1, 0, 1, 0, 0, 0, 0, 0, 0. I got one pivot variable. X1 equals negative x3. X2 is whatever. X3 is also whatever. So this equals negative t. So what is my vector? What is the solution of this homogeneous system? It's going to be t associated with the eigenvector negative 1, 0, 1. And an s is what? 0, 1, 0. So what happens here? I got two eigenvectors. So I get two eigenvectors for the price of one eigenvalue. So this here and this here are eigenvectors associated with lambda equaling 2. Alrighty.